Today we will discuss about the stabilization of a transistor circuit with respect to the change in the temperature, change in the change in transistor itself. The stabilization of a circuit is very important. Otherwise, there may be things like thermal runaway. Thermal runaway is something we should avoid. We will discuss what thermal runaway is. So let's see what is stabilization. The collector current of a transistor IC that changes rapidly when the temperature changes. Okay. So when temperature changes, the IC changes, and the IC will change when the transistor is replaced by another of the same type. This is due to the inherent variations of transistor parameters, mainly beta. Beta value actually varies from one transistor to another. Okay, even for of the same type, the beta value varies. So when temperature changes or when a transistor is replaced by another of the same type, the IC, the collector current will change. The collector current change that will produce change in VCE. Okay. So when temperature changes or the transistor is replaced, the operating point is the zero signal values of IC and VC. That will also change. Okay. But for faithful amplification, it is essential that the operating point remains fixed. For faithful amplification, it is necessary that the operating point remains fixed even when the temperature changes or when the transistor changes. So the process of making operating point independent of temperature changes or variations in transistor parameters is known as stabilization. The process of making operating point independent of temperature changes or variations in transistor parameters is known as stabilization. The stabilization of the operating point is necessary due to, as we said earlier, the temperature dependence of IC, the individual variations, it's mainly the transistor parameter variations, and then due to the thermal runaway. Okay, so due to these three factors, the stabilization is required. The temperature dependence of IC. Okay, let's understand what is the temperature dependence of IC. Here we see for a common emitter configuration, IC can be written as beta IB plus beta plus 1 ICBO, the leakage current. We have seen this equation before. So IC is beta IB plus beta plus 1 ICBO. This ICBO, this strongly depends on temperature. Small change in temperature will lead to a large change in ICBO, and that in turn will cause change in IC. So ICBO changes, the IC changes. Okay, so ICBO strongly depends on temperature, and that in turn causes the temperature dependence of IC. Okay, then the individual variations, as we change the transistor, IC changes, the stabilization is required, because we see the IC depends on beta. Okay, beta varies from one transistor to another transistor of the same type. So, due to this stabilization is required, thermal runaway. Let's discuss what is thermal runaway. We know the collector current for common emitter configuration, that is given by IC equal to beta IB plus beta plus 1 ICBO. Flow for the collector current produces heat within the transistor. As collector current flows, it produces heat, and as heat is produced, the temperature increases, so ICBO increases. Okay, ICBO increases. So as ICBO increases, the collector current IC increases. Okay, the collector current IC increases. Now, increased IC will raise the temperature of the transistor, which will in turn cause ICBO to increase. Okay, so as collector current flows, heat is generated, that will cause increase in ICBO. As ICBO increases, collector current increases. Okay, so increased collector current will raise the temperature of the transistor, which in turn will cause ICBO to increase. So this is cumulative. ICBO increases, IC increases, temperature increases. So again ICBO increases. That will cause increase in IC. So this effect is cumulative. Okay, and in a matter of seconds, the collector current may become very large. That will cause the burnout of the transistor. The transistor will burn out because large collector current flows, large amount of heat generated. This self-destruction of an unstabilized transistor is known as thermal runaway. Okay, this self-destruction of an unstabilized transistor. This happens in an unstabilized transistor. This is known as thermal runaway. Now, in order to avoid thermal runaway and consequent destruction of transistor, it is essential that operating point is stabilized. That is, stabilization is there. If stabilization is there, this thing will not happen. Okay. Now, a factor which determines the stability is the stability factor. The extent to which the biasing circuit, we use biasing circuit to give biasing to the transistor circuit, also to stabilize the circuit. The extent to which a biasing circuit is successful in achieving stabilization, that is measured by the stability factor S. Okay. So it is given by the rate of change of collector current IC with respect to collector leakage current at a constant beta. Okay, and at a constant beta and IB, this is called the stability factor. So the rate of change of IC with respect to the collector leakage current at a constant IB and beta, this is called the stability factor. Okay, in order to achieve the stability, the greater thermal stability, it is desirable to have as low stability factor as possible. Stability factor should be as small as possible. Okay, the change in IC with respect to the change in ICO should be as small as possible. Okay, because we know the change in IC due to the change in ICBO or ICO, that is causing this thermal runaway or the instability. So the change in IC with respect to ICO should be as small as possible. The ideal value of S is 1. Okay, ideal value of S is 1. If S is 1, the circuit will be highly stable. But experiments show that the values of S exceeding to 25, if S exceeds 25, it results in unsatisfactory performance of the transistor circuit. So it is desirable to keep the stability factor less than 25. Okay, practically, if it is less than 25, we can expect satisfactory performance of the transistor circuit. The general expression for the stability factor in common emitter configuration, it can be obtained. IC is beta IB plus beta plus 1 ICO. We differentiate this with respect to IC. So as we differentiate here, you will be getting 1 beta DIB by DIC, here DICO by DIC. Okay, we are differentiating with respect to IC, and this factor is actually 1 by S. Okay, because DIC by DICO is S, so this is 1 by S that we give here, and we make rearrangements, and we find S is given by this beta plus 1 by 1 minus beta DIB by DIC. The stability factor in the case of common emitter connection. Common emitter connection, is the most commonly used one. Okay. So in the last class we have seen the advantage, the base resistor biasing method. Okay, base resistor biasing method. Now let's see the advantages of base resistor biasing method. Okay, the biasing circuit in the case of base resistor biasing method, the biasing circuit is very simple, as we need only one resistance RB. Okay, one resistance RB is just needed to connect to the base. So the biasing circuit is very simple, and the biasing conditions can easily be set. The calculations are very simple. The equations that we use for finding IC and VCE, that are too simple. So biasing conditions can easily be set. Another advantage is there is no loading of the source. There is no loading of the source. Okay, the source is the source which gives the signal. Source, there is no loading of the source by the biasing circuit, since there is no resistor employed across base emitter junction. So between base and emitter there is no resistor. So there is, which usually loads the source. Loading the source means reducing the signal. Here there is no loading of the source by the biasing circuit. Disadvantages: this method provides poor stabilization. The stability factor is very high, more than 25, very high. The stability factor is very high, therefore there are strong chances of thermal runaway. So base resistor method, although it provides the biasing, the stabilization is very, very poor. Okay, so the base resistor method is seldom used, or it is very rarely used because the stabilization is very poor. Okay.